Okay, this is November 1st, 2024, Friday. I will review the set theory, what we learned for last two times, and some topics on boundness, primum, and infimum, and what is least upper bound property. And I think next time we will also discuss about well-ordering principle and mathematical induction, and maybe Archimedean property, but it will be treated next time. I will share my screen as quick as possible. Okay, first, very quick. Uh, I will speak about what I learned during the set theory. First, we learned about what is set. Set is things that you can assemble, and you can classify the elements which is in the set and which is not in the set. Which is not in the set will be complement, and there is also power set which is assemble every it is oh, there was power set which was set of all subset, and there was union. We should think about two sets, and union is set or a yeah, a union b, and there will be intersection. Both things are, you need to think about two sets, and we can speak about uh what if set is same. If set is same, then the element of A is in element of B. Element of A is in set B, and also element of set B is also in set A. And we also discuss about what is subset and what is Cartesian product of set and what is function. Function is very special relationship between the function is given, we give very special relationship in Cartesian product, and there is domain and there is codomain. When we think about function, we should think about domain and codomain, and there is range, which is set of image, and there is pre-image, which is things that is good that we can shoot to image is pre-image, and we can speak about what is injection and what is surjection. Injection is if x1 and x2 is different, then fx1 and fx2 is different. This is injection. If we go this notion to linear transformation, we can define one-to-one as linear independent, because it is same as mappings, or when x1 and x2 is different, then fx1 and fx2 is different. We can also think about onto, which is uh, range is range get grow bigger and bigger, so it became same with codomain, which is surjection. We can also think about the surjection in linear transformation situation. In linear transformation situation, the surjection will be when matrix A is able to span to B, then we will say the matrix is surjective. And there's bijective, which is when the function is able to satisfy one-to-one and onto, we will say it is bijective. And when there is bijective relationship accomplished, we can speak about what is inverse function. And there's also composition function. And we also talk about what is binary relation, equivalence relation, index family, and partition and equivalence class. That is what we did in last class. And we will, in very quick, talk about the early part of analysis. Um, Intermediate theorem first comes out. Let A be is goes to R, and there's when there is real interval, when we say there is continuous function in this a comma b period, and let's say f b is bigger than f a, then there's some r which satisfies f a in between f a and f b. Then there will be f c, some c which satisfies f c equals to r. This was intermediate value theorem. It is very intuitive. And we also discussed about number system. And this is what is least upper bound. Actually, least upper bound is, if I speak about the definition, it is what if we say the subset of real number is boundable and we say it is E, then there is beta, which is least upper bound of E, if B is an upper bound of E, and if when B is bigger than A, then A is not an upper bound of E. Then we can define least upper bound of E, and there will be supreme of E, which is B. Yeah, a set as which is subset of real number. We will say it is bounded above if some B such that for all S is B is bigger or same than X. Then we will say up bounded above, and we will say B is upper bound, same as bounded below and lower bound is defined. We can say A has an upper bound and lower bound by think of the numbers 0 to 1 over 2, 2 over 3, 3 over 4, 4 over 5. Then we can think of 1 over n is bigger than 0, so 1 minus 1 over n is smaller than 1. Then for all x, we have this relationship. So we have some relation, so we can conclude there is upper bound. In this case, consider a set, which is a subset of real number, and r is bigger than 0, and r squared is smaller than 2, of positive rational numbers whose squares are less than 2. Then A has lower bound 0. Prove that A does not have the maximum element. Then we can also do it. If we do it, then this kind of relation is we can able to make. Then A is bounded above by 2. And we will go to supremum, which is least upper bound. There is condition of two condition, which is B is an upper bound of S, and U is any upper bound of S. This is the condition. Then we will write B as supremum of X. Infimum is defined as samely. And if superbound S goes to infinite, then we will say it is unbound set. Okay. This was a very real quick analysis. And do you have anything to comment?
No. Uh, the only thing I would comment is I wouldn't. There are a lot of things that are intuitive, but there are a lot of things that seem intuitive, but aren't quite as easy to understand. Like
Mm,
they're very intuitive, but a rigorous understanding is not quite so intuitive.
right.
So I would definitely recommend doing a practice problem or two that like you already know. For example, the one example with the 1 minus 1 over n. You already know that 1 is a least lower bound.
Mm-hmm.
or rather you already know that it's a lower bound,
Mm.
I would recommend like going the extra step and proving that it's the least lowest bound or at least upper bound.
Mm, okay. And actually, there is a very small, for me, it is very big question.
Hmm.
In set theory,
Go ahead.
maybe if you have time, I will go ahead very quick.
Yeah, go ahead.
This is this part. Uh, we define equivalence class. We define partition first. Partition is there should be non-empty subset, and there should be pairwise disjoint, and there should be union covers the whole set. Then we can make partition. It is very intuitive if we think there is rectangle, and if we choose 2 point in the boundary of rectangle, and if we make a line, then it will be partition. Uh, if we think
Right.
like this, we can very intuitively understand what partition is. The problem is when it goes to equivalence class, it becomes a little bit difficult to understand for me. Like let R is S Cartesian product S be an equivalence relation on S, then the equivalence class of X under this R is the set of these. And for me, it is a bit difficult. Let R
Hmm.
be an equivalence relation on X. Yeah, equivalence relation is
Can can you scroll up to where they define that R?
they define R in here. Yeah, they
Did they not
define
mention that R anywhere else before?
right. If
Okay.
if I'm right. Yeah, they might mention R here.
Can you go ahead and send me that PDF so I can take a look at it?
Okay, I will send you a real quick. Oh, I sent the wrong file. Yep, I sent you.
Yeah, I'll need to take a look at this before I can really answer that
Okay.
real quick. Okay, could you repeat your question for me?
Okay. So, oh, I can't understand why equivalence class is defined like this. And if you go further, then there's also equivalence relation come out. And equivalence relation, the theorem 5 is about equivalence relation is actually related with partition. The problem is, I think I fail to understand what exactly equivalence class is and how it is related with equivalent relation.
Okay. Let me see. So the the set XR is equal to Y in S such that X is related to Y. Note that A is related to X is means that A is an element of XR. Implies. Um, so all that's saying is that if Y is an element of S, then it is an element of XR under the condition that X is related to Y.
Equivalence relation is defined in here. If there's reflexibility and symmetry and there's transitivity exists, then we will call it equivalence relation. And which means they both have equivalence relation. Then
Right.
if there's equivalence relation, then we can say A is element of equivalence class. And this thing, it's not really intuitive for me.
Okay. Yeah, that's
Thing, it feels like this and this is just like uh, associativity.
yeah, kind of.
Yeah, right.
It's
But
saying that
already associativity is defined in uh, symmetry or symmetry. I think symmetry is already defined in equivalence relation, but I don't know why it comes out again. Already they give equivalence relation.
I think they're just noting, like they're making the note that if A is related, or if A are X and X are both the same thing as A is an element of the equivalence class.
Mm, okay, then I think I should just memorize this. And here, then it will be for every x, which is element of equivalence relation, then x will be equivalence class or element of equivalence class. And it will be if x and y has equivalence relation, then equivalence class of x and y is equal. Wait a minute. Equivalence of x and y is equal.
Hmm.
Mm, ah, if not, I think this is opposite, not this is opposite. Eh? No,
Mm,
this
no,
is
let's think this through for a second. Okay.
okay.
So let's say pick an element S and S, right?
Okay.
If S is in the equivalent relation for X and X is equivalent to Y, like it has the equivalent relation to Y, like and S is in the equivalent class of S, by the transitive property, which is explicitly stated, it's kind of being give given here, kind of.
Mm-hmm.
By the transitive property, S would be in Y, is what this is saying.
Mm,
So if an element is in the equivalence class, and then the two equivalent classes are related,
mm-hmm.
that element in one equivalence class would be in the other. By contrast, number three is saying if they're not equivalence classes, if one is in it, it's not in the other.
Mm. Can you say about second thing once again? This part?
So let me read real quick and make sure I'm saying things right. Okay, so if X is related to Y by R
Mm-hmm.
and an element S is in the equivalence class of X under R, then S would also be equivalent. Then that implies that S is equivalent to X under R, correct?
Right.
So then if S is equivalent to X and X is equivalent to Y, then S is equivalent to Y
Uh,
under R.
okay, I got it. Mm. If X and Y has equivalence relation, then
How are you reading number three? Real quick.
I will try it. If X and Y has equivalence relation, then
Okay,
equivalent.
so number three says if X is not related to Y under R.
Yeah.
It's kind of hard to see, but there's that slash.
Uh, if X is not equivalent to Y, then equivalence class of X and Y, intersection of X and Y has no element. Now things are get correct. Think I understand it right now. And theorem 5 and 6 is highlighted, and this is the final of set theory. Theorem 5 is about what it's saying is let S be a set and let R be an equivalence relation on S. Define the set of equivalence classes. Then P performs a partition of S. It's like equivalence set of equivalence class is partition.
Right.
And if I go to this, then
Let's work on theorem five first, because typically the
mhm,
way these the way these papers works is you prove theorem five to prove theorem six. There are some exceptions, but that's typically going to be.
mhm. Okay, then I will read the proof. We must show that the set of equivalence class satisfies the three conditions of partition. Equivalence class is not empty. Disjoint. Hmm. If X is equivalence class under R, then we can say X and X has equivalence relation. Where yeah. Oh, XR is defined like this. So X and we can say X and Y has equivalence relation. Then
Mm.
it is not empty because hmm, I think the number three is it's by definition because they define equivalence class like this. So mm, I think I need to study more of this part.
So you're do you get part one of the proof? The equivalence class is not empty.
Oh, I think so uh because X is in S, equivalence class
Hmm.
not empty.
Yeah, so that's just coming straight from lemma 4.
Mm.
And then equivalence classes are disjoint is also coming from lemma 4. That was the if if two equivalence classes share any elements, they share all elements. And if
Mm-hmm.
they don't share any elements, they're disjointed.
Yeah.
That's the abbreviated version. And so you already have part one and two of proving that the set of equivalence classes is a partition. So you just need the union of equivalence classes is the whole set.
Mm.
So that's what. So now you're on part three.
Mm.
So you need to show that the union is the whole set. That's what you need to show. Um, and then by definition, um, an individual equivalence class is a subset. That that's just by definition.
Mm.
Um, so you have that the union of equivalence classes is a subset, is at most a subset
Yeah, right. So
of
it will
S.
be the same thing because you will get the whole subset, then it will become whole set.
Right, like a union of subsets can't be more than the set.
Mm. Okay. Then if we go to theorem 6, that is like kind of reverse theorem, which is let S be a set. And if we make partition partition be a partition of S, then we define a relation R on S, which is X hash relation or not hash relation with Ri. Then it is same with I, which is element of I, such that Xy is partition I. There is X related to Y under R if and only if X and Y belong to the same subset Pi in the partition. Then R is equivalence relation induced by the partition P. Yeah, this is what.
Yeah, so let's give you an intuition for why this is true. Okay, so it's saying if X is related to Y,
Mm-hmm.
like to just blow past the confusing notation, if X is related to Y under R,
Mm-hmm.
then they're both part of the same equivalence class, right?
Mm-hmm.
Which would mean they'd both be part of the same partition.
Uh, yeah, I understand it.
So that's all that line is saying, and that's what it's saying in like notation.
Mm-hmm.
So now we need to prove that because like yes, we have the intuition for that, but we don't have a rigorous proof.
Mm-hmm. So in the note, we use reflexibility, symmetry, and transitivity. X is element of S, and by that union of partition becomes S, we can say X is element of partition union of partition I. Then some I, something that X is in partition I, then we can come out with X and X hash relation. And
Right.
we can also derive y and x has a relation under R based on using symmetry. No, based on when I is substitute I, then we can say y is substitute pi and x is substitute pi. And intransitivity, we use x and y has relation and y has z has relation under R. Then we can use x is x which is in pi and y which is in pi. When y is in pi and z is in pi by b, which is pi and pj is has no common element when I and j is different. We're using that, then make we can say some I equals to
I
j.
don't think that should be sum a. I don't think that should be sum I. I think that should just be I equals j
Mm,
because it being sum I does not make sense.
mm. I and when some situation I and j is equal to I, then something that x is in pi and g is in pi. So we can say x is has relation with z. Mm.
Right.
I think maybe if it is possible, I need to reorganize this theorem 5 and 6. But right now, I finished. And if I sum up, uh, do you think if I want to study deeply with algebraic things, then is it enough to finish set theory with these things?
You're asking like, would finishing all of this be enough to have a good grasp on algebra?
Right?
Mm, no, unfortunately.
Mm,
The big thing that makes algebras is you have your set, and then
mm,
you also have an operation attached to that set.
mm,
So like the standard algebra that everyone learns throughout
mm,
school is the real numbers with addition and multiplication.
mm,
Um, and then as you go farther, you learn the complex numbers with addition, multiplication, and maybe another set. But especially modern algebras,
mm.
eh, the operations become no longer set. So you would be defining your operations for each
As
type of
operation, not
algebra.
offset.
Right. So as an example, a group is one operation with a
Mm,
set. So the integers under addition is a group,
mm,
and you do algebra on that group.
mm.
Just a set on its own, while it is a building block of algebras, is not sufficient to do algebras.
No. For the group, I think I will be back with the content after some analysis.
Mm.
There will be some abstract algebra regarding group, field, and these things after some analysis. So I think I can prepare things, and when I do operation things, I can maybe uh, organize this set theory again.
Right.
Okay. Then for today, thank you for participation. I will stop the recording.
Thank you for having me.
No, okay. Thank you for always participation. And Jonathan, mm, do you have anything you want to do in this? Oh, wait a minute. Recording is not finished.